when 8 Russian missiles streaked into the air. None of them hit what they thought they were aiming at. The Pantsir S-1 launcher had locked onto 6 fast-moving signals. Only 4 of them were real threats, or so it believed. In those few seconds of confusion, Ukrainian operators quietly guided 2 actual attack drones under radar cover, weaving through trees at 10 meters altitude. What happens when a $3 million defense system wastes its entire volley on $200 decoys? That's the riddle this mission answered, and it changed how both sides see drone warfare. Before we move on, please take a moment to subscribe to the channel and like the video. It began far from the front lines, inside a windowless control room, lit only by the pale hum of monitors. 4 Ukrainian drone operators from the Ronin unit leaned over their consoles, each screen showing a grainy feed in faded greens and grays. Their target was moving somewhere beyond the horizon, a Russian fuel train that had been running fuel north to supply armored units near the border. Taking it out wouldn't stop the entire operation, but it would choke a critical artery feeding the Russian logistics chain. 35 kilometers stood between the operators and that train, across a territory buzzing with electronic warfare designed to blind anything unmanned. The Russians had built a wall of interference using R330ZHZ jamming systems, spreading a dome of static over wide areas. That machine, mounted on heavy trucks, could reach across 15 kilometers and distort every signal from 100 to 2,000 megahertz. To most drones, it was a death sentence. Control vanished, communication severed, and flight software forced into failsafe mode. The Ronin unit knew the only way through was old-fashioned frequency agility, not software wizardry. They set their drones to use analog 5.8 gigahertz channels, avoiding the digital signal processing that caused precious input delays. A quarter of a second might not sound long, but at 80 kilometers per hour, that delay could mean missing the train by several meters. Analog feeds carried no built-in error correction, so the image on screen often cracked, skipped, or vanished into snow. The advantage was instant response. When an operator leaned the joystick, the drone responded immediately. To carry that fragile signal across the jamming bubble, engineers launched a relay chain of repeaters. 3 main drones hovered at staggered altitudes, one at 500 meters for clean line of sight, another at 200, and a backup just 100 meters off the ground. Each acted as a node, catching one stream and passing it on like a whispered message in a storm. 2 extra backups waited further back in case one fell. Once the chain stabilized, the attack drones accelerated, tracing a path along the same rail network that fed their target. The operators had memorized every landmark along that route, river crossings, clusters of birch trees, the curvature of the rails leading into a shallow valley. During training, they had spent hours in simulators, losing their video feed on purpose. They practiced counting seconds between visible waypoints, teaching themselves to fly blind for up to 30 seconds if interference cut their view. On comms, one pilot muttered prompts under his breath. Count to 15, slight right, aim for the power line tower. Every breath mattered, because if drift began, the drone could veer off into open sky and vanish from control forever. As the drones passed the 25-kilometer mark, the first signs of exposure began. Russian sensors along the rail corridor detected faint electromagnetic signatures jumping across the frequencies. Operators at a Kasuka monitoring post noticed erratic blips, but they couldn't fix altitude or bearing. The Ukrainian team kept their drones low, threading between treetops, letting the terrain mask most reflections. Despite the static, one pilot nudged his stick to compensate for crosswind, relying entirely on mental mapping. Each second demanded perfect coordination. A slip meant losing a $3,000 drone to an unseen forest or a jamming spike. The discipline came from repetitive drills under degraded feeds. Working inside interference rings during training, the Ronin pilots learned to filter chaos into routine. When screens turned to snow, they didn't panic. They adjusted throttle, trusted timing, and waited for signal reacquisition. Years of practice reduced fear to math. They were almost through when a wide radar sweep flared across the spectrum, revealing that the Russians had locked on. Somewhere ahead, a tracking array was already aligning. The operators could see nothing on their screens but static and a flickering cursor. The calm before the start of an aerial chess match that both sides knew could last only seconds. The instant Russia's Kasuga-4 picked up the faint control signals, the quiet night over the rail corridor shifted from routine to alert mode. The system's sensors, capable of detecting emissions from 150 kilometers away, caught multiple returns rising from the tree line. The signal analysts flagged the activity to a nearby Pantsir S-1 crew, a self-propelled air defense system known for its rapid-fire response. In less than 10 seconds, the Pantsir's radar began narrowing its scan, identifying 6 distinct echoes, closing fast across the boundary zone. At this stage, the defense chain was pure automation. Data from Kasuga-4 passed through encrypted communication lines, feeding into the Pantsir's fire control computer. The algorithm set to work calculating speed, trajectory, and radar cross-sections. Within 8 seconds, the system had a firing solution ready, but the decision was unclear. Were all 6 returns real? Inside that moment of indecision lay the thin edge between efficiency and waste. If the targeting computer misread the situation, it would burn through millions in munitions on harmless signals. If it waited too long, a real drone could breach the perimeter and destroy a fuel line that fed hundreds of armored vehicles ahead. Every fraction of a second mattered, and the Russians knew it. Ukrainian planners, though, had studied these fire control patterns for months. They understood how the Pantsir's radar prioritized targets, size and intensity over erratic motion. So they prepared their own answer: 6 cheap decoy drones, assembled for barely $200 each carrying a small corner reflector made from aluminum panels shaped to bounce radar waves back stronger than their frame should allow. As the decoys entered detection range, they lit up on radar as large, confident targets. 4 of the 6 reflectors functioned perfectly, while 2 failed to stabilize and started losing altitude. On the Pantsir's screen, though, that distinction blurred. The defense computer interpreted the strongest 4 as immediate threats and assigned each a missile lock. Operators approved the intercept sequence automatically. 8 missiles launched in rapid pairs, streaking into the sky at twice the speed of sound. Each missile cost more than an apartment in Moscow. Yet within seconds, they were chasing signals that were little more than scrap parts and solder. The Ukrainian command watched through what little video feed survived across the interference zone. A brief flash showed one decoy flipping midair before fragments of metal rained over the forest. But the pilots didn't need to see. They could feel through timing alone that the defense network had committed its strike too early. While Russian radar processed the exploding debris as successful intercepts, the 2 actual strike drones descended to 10 meters, hugging ground contours that blurred them into ambient noise. They used every meter of terrain masking available, following power lines that created natural electromagnetic clutter. Frequency hopping added another layer of confusion, their signals darting from one clear channel to the next before the Kasuga unit could adjust its filters. Milliseconds of chaos set in. The defense algorithm attempted to rescan, but could not reconcile reflections from multiple altitudes. Ground interference swamped everything below 15 meters, the radar's minimum effective limit. That small gap turned the low-flying drones into ghosts. Russian operators, aware of their remaining 4 missiles and the reload time of nearly 20 minutes, held fire. They waited for clearer confirmation, but none came. The system's logic tree faltered, classifying the airspace as neutral noise. Meanwhile, the 2 attack drones accelerated again, climbing only when terrain demanded it, still tracking the faint metal glint of the railway ahead. Cheap drones didn't just hit a train. They rewrote the cost balance of modern war. A small team with parts costing less than a used car dismantled a multi-million-dollar defense system by forcing it to waste precision missiles on decoys. The success wasn't luck. It was careful planning, coordination, and a deep understanding of how machines interpret noise and order. Military analysts now see decoy swarms as tools that can reshape future battlefields. If today's improvised drones can blind complex air defenses, the next generation of low-cost autonomous systems could redefine power, strategy, and the meaning of control in warfare.